Thank you all for coming. And I want to, I'm Gary Hine. I'm the director of the Dr. Klein Health Program. And I want to welcome you here today for Chris's final seminar for the Dr. Klein Health. This is one of the last requirements that he needs to complete. I guess he hasn't completed it yet. He needs to complete before finishing up. So he has got a short introduction for himself that he's included in there. Chris got his bachelor's degree here at UNL in 2017, followed up later during the DPH program with Sam Wortman, getting a master's degree as well. So I'll let him introduce himself a little bit more and take it away, Chris.
Okay, thank you, Dr. Hine, for your introduction. Okay, so good morning, everyone. Welcome to my final final seminar for the DPH program. It's such an honor to be here to give a presentation. I see so many familiar faces, friends, family, colleagues that we worked for so long. It just surprised me. I see so many familiar faces that I really appreciate your presence here. So the title for my presentation today is Image Analysis and Machine Learning in Agricultural Research. Before I go into the presentation, I want to give you guys some of my background. So I was born and raised in Beijing, China. It's a long drive from Beijing to Nebraska. As an urban kid, I not compared to other kids, I'm always passionate about agriculture, specifically specialty crops. That's always been my passion. That triggers me to move to Nebraska to pursue my further degree. So back in 2017, May, I graduated with a horticulture degree, bachelor degree in horticulture. And after that, I want to further advance myself. So I was lucky to get admitted by the DPH program. And shortly after that, I took a bunch of classes with other graduate students, and that really made me into doing research. So I was really lucky. I got accepted by Dr. Wortman 3 years ago. I was able to complete a master's degree with him. And he has been the best mentor for me. I learned a lot from him. My thesis is I work with herbicides specific dicamba 2,4-D, lettuce and pumpkin. So you can look at my thesis on Progress if you're interested. For my internship that I require for the DPH program, I complete both internship at RD4Ag. RD4Ag is, I would say, one of the best contract research company here in the United States. It's located in Yuma, Arizona. Yuma is, if you go to Arizona, it's down to the south, closer to Sonora, which is Mexico. So from Yuma, if you drive 20 minutes, you're in Mexico. So it's really close to Mexico. I was lucky to do 2 internships at 2 different seasons. So last year, fall is winter. So I get to work with leafy green, specifically lettuce, cauliflower, broccoli, spinach, etc. And in the summer, I got to work with completely different crops. I work with melons, tomatoes, peppers, all of the fruiting crops, which is really exciting. My job title at RD4Ag is research biologist. So I'm a project manager for a few different trials, which including pesticide efficacy, crop protectants, growth stimulators, and herbicides. When doing those kind of research, I was in charge of evaluating many variables, such as insect weed population, disease level, and pest physiology, etc. I want to talk about, when we collect data by our human, there are certain pitfalls that involve it. The first pitfall that I want to mention will be, humans are subjective. Specifically, Koch and Hall 1980 defined that before we're even doing this kind of evaluation, we might have a preferred value when doing the disease assessment. This is not ideal, when we're collecting data before even we see the symptom where we have a number in our mind. Another example is rater bias. Sometimes one of the example would be when you do the evaluation of citrus canker foliar evaluation. This is an example. If you see a loss of lesion number on leaves, you tend to overestimate the percentage of chlorosis or the percentage of necrotic area, which is also not ideal for collecting data. Second pitfalls will be, humans are fragile. We might have this kind of experience working in the field when there's lightning, rain, or wind. That definitely makes us uncomfortable in that situation collecting data. In addition, sometimes when we work with chemicals that are highly toxic. This including, class organophosphate. Some literature you say, exposure to this class of pesticide, sometimes you're exposed yourself to a cardiovascular disease or might be cancer, in some worse situation like that. So that will be one of the other pitfalls. Third one would be, humans are available with limited attention span. One of the examples is you are, collecting data. Sometimes you get a phone call from your colleagues, you talk to somebody, then you get distracted. Or sometimes you get bored, you're doing that for a long time, you get bored. Those, you cannot avoid making mistakes. This mistake including overwriting data, typos, incorrectly copy and paste. If you don't pay attention and you did it wrong, and then 3 or 4 days later, there's no way you can recover it, because if you made this mistake, typing on iPad, you cannot recover it, which is also a problem. Also, long hours of scoring plans, you might just get tired. Fatigue will come in. You feel you might make more mistakes. Lastly, human can be slow, especially working at contract research, or other research that we do. If you're in charge of evaluating many plots, you might have you have to take a moment to think, and then typing that will, working around the field, that will take a lot of time. So it can be slow, collecting data by human. So of all of the 4 issues, what we can do, I would say, hey, image analysis could be one of the solutions. So for my doctoral document, I separate by 3 chapters. So my outline will be chapter 1 is more of the essential background you need to know about image analysis. Moving to chapter 2 is more of a case study, application you can use in different situations that you can use image analysis and machine learning. And the last chapter is I went off and beyond. I did something myself. It's my own case study, because I was interested in, how about I learned something about machine learning that can automatically grade for quality, especially for lattice, bolting, and compactness. So this is the general outline for my presentation. Moving on to the first chapter will be the essential background. I will divide into several sections, including type of images, image capturing, process of image analysis, and machine learning. For type of images, visible light image is probably one of the common use image in our daily life. The wavelengths for visible light image is in between 400 and 700. This is the visible spectrum in the spectrum level. That's how our eye can see. RGB is red, green, blue is one of the type of image that are commonly used. For example, if you use your cell phone to take an image, those images are RGB image. So here's the full color of the image that will divide by red, green, and blue channel. So those 3 channels will combine together and mix different colors. One of the example will be, this garlic is white color. To make white color, you need to have about the same intensity of red, green, and blue. This is the example, to make the white color. To see the image, you have to look at the pixel. So white is the pixel number. This is for analysis to tell you the matrix where it's located. So intensity, you have to have 3 different intensity levels at the same level to make white. There's just one of the examples I want to show. Hyperspectral image is the second most used image for image analysis. Hyperspectral image is measuring the wavelength in between 400 and 2500 nanometers. So pay attention, the wavelength is continuous. So this is the example, you're measuring the continuous in between that wavelength. Because you're measuring the full wavelength based on the reflectance, hyperspectral image can detect really subtle, reflectance, including, you can use that for measuring biochemical attributes, which including chlorophyll, sugar, amino acid, etc. Or you can also do biophysical attributes. This including more of the physical structure of your plants, including, the height, the leaf angle, different parameter in that situation. Multispectral image is similar to hyperspectral image, but it's more of a subset of the hyperspectral image. Compared to you measure the continuous wavelengths in between this whole range, it only measures, the very few distinct spectral channels. Those channels including red, blue, green channels, or you have near infrared, shortwave infrared, or infrared, etc. because of the limited, channel you're measuring, so the evaluation can be not as strong as hyperspectral image. However, there are certain index that you can use to do this kind of evaluation. One of the examples I want to mention would be normalized difference vegetation index, also known as NDVI. Some of you guys probably know this already. So NDVI is commonly used in remote sensing, also in small plot research. The concept behind is you can use NDVI to measure the chlorophyll contents. The concept behind is when the light, because the plants, they can absorb red and blue light. On the other hand, they can reflect near infrared and green light. So here is the formula that based on the parameter you can measure, you can come with NDVI. To more visual, see the differences. So NDVI is more greener the color, the higher the NDVI. So here's the example, here is more green. The number will be closer to 1 compared to when you're more of red color, it tells you the number is around 0.18. So this is very useful to tell you, the standing situation in your plant, where you have a good stand and where you have a poor plant stand. So you can make decision in that way. Lastly, I'm going to talk about thermal image. Thermal image is quite, self-explanatory because they're detected temperature differences. They measure the thermal infrared regions. One of this is the image I want to show. On the top, you have well weather condition for your corn. On the bottom, you have drought stress. So based on the color, cold color or warm color, you're able to separate the differences between whether they're drought stress or not. So the application using thermal image, including you can predict water stress. You can also planning for irrigation schedules. On the other hand, some of the disease and pests, when they're infecting plants can actually be harder compared to their not stress. So in that situation, sometimes you can use for disease and pest detection, for example, for using thermal imaging. Next, we're moving to image capturing. Image capturing is the way you want to ensure the quality of your image. What you can do is first you can control the background. Here is an example. This is not a good example. You're taking an image of a leaf, but you have a really busy background behind. There are excessive green pixels behind. So when you're taking this image for the evaluation for lesion numbers, this is not ideal because the background is really busy. It's really hard to bring the contrast of what you're interested. So using color distinctly different than green is a good way to take an image. For example, at RD4Ag, we recently coming with this idea. How about we use pink color? Pink is opposite of green. You rarely see pink in field. So especially vegetable, you rarely see pink color. So we came up with this idea. How about we use pink background? That works really well. We started a couple months ago. We're continuing using this because it's easier to contrast the color and segment out what you're interested. Control of lighting condition is also important. At RD4Ag, we have this mobile cart. You can wheel around. On the top, we have a singing bar. We can move around in the field. We give them a nickname called Carzella. So it's really cool. We can put the shadow cloth on top, and then we have our camera mounted here, and with the clicker. So now we can just take an image that way, and always at the constant height, you can adjust it. So the shadow cloth is very useful because it will create this diffusive light, and that will prevent the shadow condition, which is very useful when collecting image in the field. Another example, important thing will be control of the objects. Here is an example. My friends is doing the evaluation, plant growth evaluation on peppers. So we have this selfie stick. Before we take the image, we always spray paint the specific spot. And the selfie stick is at a constant height. So we want to make sure the exact same spot, exactly same height. So we'll take a different time point at the same spot. This example just show you constant height is very important. And also the exact same spot, you can do that to control your objects. Another example will be using non-reflective glasses. For example, if we're taking image, that one of the image I show you that we're taking image of leaves. Leaves, they're not always perfectly flat. If we can use a non-reflective glass to overlay on top, that will actually make you take a better image. Okay, now we're moving on to the, the step of image analysis, which is the key thing that, for my presentation, the step of different image analysis. First step will be image processing. Image processing will be, you want to bring the contrast of your object of interest. First one will be denoising. So here's the example. We're taking a Arabidopsis plants. This is not a good, it's not a perfect lighting condition. You're taking this image when there's poor lighting. So there's like some noise at the back. You can apply certain algorithm to remove the noise. One of the common used one would be Gaussian classification. And here's an example, you can remove the noise this way. Another example is you can resizing on the resolution. When you take image, you always want to have constant resolution. This is important. You definitely don't want to have one image has higher resolution than the other. So you can apply in image analysis, you can actually, there's an example, you can reduce the pixel by half, or you can set specific resolution you want. Cropping is another example. Sometimes you take an image that has lots of like what you're interested. So occasionally you have to crop some of the image out. So here's an example, you can use cropping. Stitching is another example. If you're meshing a really long plot, for example, you have a GoPro that you can set it every second you take an image. So you can walk around the field every second you take an image, and you can stitch them together. That will give you a better representation of the whole field. Is also very important. Lastly, increase image features. Here's the example that the image has with lots of shadowing. So really hard to see what you're looking into, the image of contrast. You can see on the histogram, most of the color ranges in between 70 or 150. So they're like clustered together. That makes sense. You cannot bring the contrast. So what you can do, you can apply histogram equalization by stretch some of the pixels. And here's the example by applying histogram equalization, you actually can see the feature you're interested. In addition, brightness, another example, you can also play with the brightness. That will also bring what you're interested out. Segmentation is the second step for image processing. Segmentation is by definition, they're grouping similar pixels based on the intensity, the texture, or color. That will allow you to divide image in the different regions of interest. Here's an example. I acquired this image from one of my professors at Dr. Chowdhury. She gave me this image. So I played it on my lab. So I was able to segment it by color. I was segmented only the color green and also only the color yellow. And based on that, because this is the Arabidopsis has natural senescence, I was able to tell there are 22% of senescence area. This will give me a more objective, compared to subjective, you say this may be like 10%. Now I know for sure it's 22% senescence area. Feature extraction is the last step for image analysis. What you can do is you can extract the features based on the shape. And here's an example, in woody plant, you have different shape of leaves. Another example will be edge detection. Edge detection is based on the abrupt change in brightness or color. Here is not a good example, and I mentioned with a busy background. So that's why when you do apply this abrupt change in color or brightness, you still have that kind of really busy background. But this gives you a picture, how you can do edge detection. So you can actually segment it, general structure of the plant you're interested. Texture is another feature you can do analysis. Texture for us, you can feel the texture by touching something. However, for image, the texture is defined by specific distribution pattern of pixels, or also dispersion intensity of the pixels. Here's an example. If you walk around plant science, look at the tree, the leaf falling down the ground. You look at the maple leaves, they overstack on each other. It kind of give you this texture feeling because there are specific distribution pattern of pixels. And also, if you look at the turf, they also give you that kind of, feeling of texture. So here's just a image I want to show, how you can see the texture in an image. And color is another one, you can do feature analysis as well. One of the example that we did at RD4Ag is we are doing the shape analysis. So here's the example. We have baby leaf lettuce. We have, the baby leaf lettuce, depending on the variety, they have different shape features. So by taking the image of baby leaf lettuce, we create the binary image, which is, only the leaves. And then we can apply analysis based on the width and the length, all the shape analysis on the lettuce. After that, we can successfully, detect the differences between three varieties. And this is the research we actually try fertilizer study, reduce the fertilizer by half. We want to see how the fertilizer will affect the features. So here's a chart I want just like to show how you can do this kind of analysis. Okay. Lastly, for image analysis, the essential information will be machine learning. I'm not really an expert in machine learning, but machine learning, the first one will be the unsupervised machine learning. Unsupervised machine learning do not require label data. What you can do is you can apply this called K-clustering based on the pattern in your data, either by color, all the features that I talked before, they can actually automatically detect and cluster them by different group. So this way, this is the unsupervised machine learning. Moving on to supervised machine learning. Supervised machine learning needs to supervise. So they require label data, which is the data, you have the image and you also label the image, what you're looking into. For example, you might have an image of insects. You want to tell the label the information, how many insects you can see on this specific image. Those are the label data. There are two types of machine learning, supervised machine learning. First one will be the regression. Regression will be you can count the insect on an image because there are numbers and they're a continuous number. Another way will be classification. Classification is the result of categorical. So you have yes or no, or you have different levels of severity. For example, 1, 2, 3, 4, 5, you might have different severity. So this is in general information for machine learning. Now we know all the information for image analysis. Let's move on to second chapter, which is my case study. For my case study, I divided by different scenario. First one will be leaf damage evaluation, moving on to stress detection and plant growth, and lastly will be counting. For leaf damage evaluation, this is the similar example that I did with the Arabidopsis plants with natural senescence. Here we are measuring the chlorosis. So image A will be healthy plants, B will be slightly chlorotic, and C will be not really chlorotic. It will be more severe chlorotic, excuse me. So here's an example. You can do the color segmentation, but what you can do, you can also separate the full image by different sections. For example, if you have a bigger image, it will be applicable. You can separate the image by different sections for analysis. Another example of using RGB image for leaf damage evaluation, I think this is one of the cool example. You can actually measure the leaf deformation. So this paper pairing with Pratt 2001, they came out with this formula. Here's the example. You have healthy non-deformed leaves, you have slightly deformed leaves, and you have really severe deformed leaves. So what you can measure based on this formula is you only need to measure two parameters, which is the leaf area and the perimeter of the leaves. You can come with this deformation index based on this research. What they came out with, what the results showing, closer to 1 will be healthy non-deformed leaf. However, if you go on higher number, the deformation severity will be higher. So this is really cool. I never thought you can use RG image to do, deformation on leaves, which is really cool idea I want to share with you guys. Another example will be using spectral image for disease the identification. This is based on when the light strike an object, the reflectance are a little different. What the literature find is they can on hyperspectral image, they can measure the disease detection. The perfect wavelength will be in between 400 to 100 nanometer. Difference in reflectance can be used to identify disease. One of the examples I want to show is here we have powdery mildew, rust, and leaf spots. If you look into the image, you see they have slightly difference in the structure. For powdery mildew, they only go into the epidermis, they're not going to deeper inside. For rust, they create this episorium, so they actually penetrate inside and go deeper. However, for leaf spot, they will not only go inside, but they release the the enzyme, they start to rot, degrade the structure. So based on the reflectance, you can clearly see because the internal structure is different. So using hyperspectral camera, you can actually detect the slightly different in the reflectance. So one of the research they find is they're using this hyperspectral image, matching the wavelength in between 400 to 2500. One of the examples they did is they are matching on wheat plants. So here we have a healthy wheat plant. We have a night blotch, rust, and powdery mildew. Based on the reflectance, they create these things called unique spectral signature. And every single signature is specific wave, the reflectance that they have matched with specific disease. It's called the spectral signature. So here's the example, they have different signature for healthy night blotch, rust, or powdery mildew. What the research found, at about 100 nanometer is perfect to separate powdery mildew and healthy plants. However, the night blotch and rust overlap, so it's hard to separate. But you can look at the wavelength at 700. That will allow you to separate the night blotch and rust. Here's just one of the examples, how you can use hyperspectral image based on the unique spectral signature to identify specific disease. Moving on to stress detection. Here is an example of a soybean plant that has iron deficiency. One of the examples you can do is on this paper is they're defining yellow and green pixels considered as healthy area. However, you have brown area will consider as iron deficient. First, you do the segmentation based on the color, and then the paper came up with the reading like scheme for iron deficiency in soybeans. So reading 1 will be healthy, 2 and 3 will be slightly iron deficient, and then you have reading 4 and 5. They're shown as more brownish color. They're more severe with iron deficiency. Applying a machine learning algorithm, this will be the classification algorithm. They can actually really accurately detect the iron deficiency at the accuracy of 96%, which is pretty good. Another example of the stress detection will be using thermal imaging. Here's an example of, I showed this image before. You can use thermal image to see the temperature differences. However, for this image, you have 4 days and 12 days. You have a well weather condition, you have a drought condition. But this is not a good example because they're taking image not at the same angle, same height, because the second 12 days to take a different angle. So if you just look at the image, you might say, 12 days is not as severe as 4 days because 12 days has more like colder color. So just emphasize, it's important to constantly take at the same angle, same height. But when doing this kind of analysis by analyze the colder temperature, the colder color and the warmer color, you're actually able to separate either you're in control or in drought condition. 12 days is the perfect day. You can actually see the clearly difference between control and drought. By measuring the specific dispersion of the red pixels, you're able to identify, for example, this research, they identify corn genotype with drought tolerance. So if the red pixel is more dispersed at higher number, this means they're really susceptible to drought. However, if they're more narrow, like not as dispersed, they're showing that variety is more drought tolerant. Let's move on to plant growth evaluation. Plant growth evaluation is something we always do in our research. You want to know like how well the plants could do, So here's the image that I already flagged that I mentioned before. We use a selfie stick. We always take as exact same spot, same height. So here are the example of image you acquire using the selfie stick. One of the examples we're showing is we're trying to measure the growth of strawberry. So we're taking a overhead pictures. We can use ImageJ, which is an open source image analysis software. First step is you can import the image into the ImageJ, and you can do color threshold by playing with RGB image. They have red, green, and blue channels. You can actually zoom like specific to the green pixels. After that, we can create a binary. You can clearly see the boost is automatically gone because it's not a green color. So we're only looking for a green color. but we still have some green pixels because those are maybe some weed on our plot. So what we can do is we can either manually remove the noises, or you can actually set this is our plot, and then we can automatically just remove all the pixels outside the field. After that, you can, using the site measurement on image J by measuring the area, that actually give you the area of the pixels, of the green pixels. If you do it at different time point, you can actually, for example, you're doing 3 days after planting compared to a month after planting, you take the image, there will be clearly difference. So you can actually measure the relative growth basing on taking the image at different time points. Here's just an example, how we take a good image with a selfie stick. But pay attention, it's really critical to control within the plot. You want to make sure there's not a lot of weed, because if you have a lot of weed in the plot when you take image, there's no way you can remove that pixel. So it's really important to clean the weed within the plot when you do this kind of evaluation. Counting, some of us work with insect, it's always really hard to count insect. It's really, really tedious, and you have to play with a microscope, and it's really time consuming. So at RD4Ag, we also did a lot of insect counting. Here's an example is we use a leaf puncture. We take the leaf puncture on pumpkin. This is one example. And then we collect this disc, but then we collect them in the ice chest. We move them back to our office, and then we look them under the microscope. It takes a lot of time for us to count those insects. So one day, my friend's Connor, he say, how about we try using a printer scanner? So we can, instead of looking with microscope, playing, how to mess around with microscope, how about we just scan it? So we came up with this idea of printer scanner to scan for your leaf disc. And it worked really well. But one of the problem is with a printer scanner, if you set a really high resolution, it takes 5 minutes to scan the image. And also the size of the file is huge. It's 150 megabytes for that image. So it takes the computer forever to open it. So we also come up with this function on image J. You can actually cut through the image by 4 sections, and that will reduce the file size to about 30 megabytes, 40 megabytes. So it's a lot quicker for them to open it. And this method worked really well because now you don't have to look under the microscope. It saves our time by half. And now moving on to one of the examples that you can actually do machine learning and image analysis on counting insects. Here's an example. We're looking for the black pine bat scale, which is a small diptera insect. They're really small. This research actually, they take image of from the sticky trap. So first they set the trap in the field, and then they take them back to the indoor condition. They will take image, and then they will have ask professional to label those image based on either the training set or validation set. Training set for training, validation, they want to test the accuracy. After that, they will feed into the CNN network. Based on using feature extraction, they can look into shape, color, texture, and edge. Doing that, you're able to identify insects in this example, and we can do counting and then the accuracy test. Accuracy tests for this machine learning counting insects, they're actually really high because they use a couple of thousand images for training. The accuracy is 95%. However, for the 5% inaccurate that I want to show is for the red box is you can actually correctly identify the insects. However, there are issues with false negative. False negative would be sometimes you have, when you're collecting data with sticky trap, sometimes we have insect overlay on each other. And here's the example, we have 3 insect overlay on each other. We can probably see by our eye, but machine learning, they wouldn't able, based on the feature of the shape, they're not able to identify. So this is one of the false negative you can see. In addition, you might have false positive. False positive would be, here's an example, you only have wing, like part of the insect, but they were falsely identified as an insect. So those are some of the areas you can see when doing image and doing machine learning specifically. Now we're done with first chapter, the essential background, the case study. Let's move on to the third chapter, which is my own case study. I want to come up with a machine learning algorithm to automatically detect bolting and compactness. I wrote this chapter based on the typical research paper, including introduction, material and method, and result and discussion. Just a little bit background of lettuce production in Yuma. Lettuce in Yuma is direct seeded. Depending on the variety, specific for the romaine lettuce, you have early mature variety or late maturity. So the time is for mature is in between 75 days to 105 days. In Yuma, Arizona, we grow about 20,000 acres of romaine and also 10,000 acres of baby leaf romaine. Yuma is also known as the winter salad bowl of the United States. So the production in Yuma is around November to early April. Yuma is very important because they produce 25% of lettuce in the entire nation. So it's very important location to grow lettuce. For measuring lettuce, specific romaine, you look into different quality measurement. First of all, will be compactness. Compactness is you're looking at the internal density of your lettuce. The marketable romaine is relatively tight, so they're relatively heavy. You want them, the leaf are more condensed to each other. And there are 5 levels for compactness. The first one will be level 1, is you can see it's open and loose. And compactness 2, you see there are some compactness at the bottom, but the top is open, but not as tight. Moving on, level 3 is marginal. You see it's relatively tight at the bottom, and on the top they start to form. They're getting tight. Level 4 is the ideal. The perfect example of compactness. You want your lettuce to be relatively dense at the bottom, also on top. You see those overlay on each other. This is a perfect example for the perfect compactness. However, moving on level 5 is too compact because they're a little bit more mature. You don't want to harvest when they're too compact because the leaves are getting more thicker. When you eat them, they're not as tasty as level 4. Another quality you want to see in romaine is the bolting. Bolting is another parameter you measure the quality. Bolting is measuring, this is the future flower stalk. It's also known as the bud end, which is this part. If you let this lettuce grow in the field, they will start to grow up, and then they will show this flower stalk. You definitely don't want to grow your lettuce, to bolting because you're not harvesting seeds. Bolting really affects the taste of your lettuce. It will make it more bitter, so really undesirable for us to consume. And there are also 5 levels for bolting. Bolting, you want to look at into the bud end that I mentioned before. You want them to be rounded on top. You don't want them to get pointy. So the perfect example will be 1 and 2. They're rounded right here, so which means they're not bolting at all. And based on the length, here's the example for 1 inch length. Level 2 will be 2 inch length. So both 1 and 2, because they're rounded here, it means they're not bolting. So they're a perfect example for marketable. However, 3 is more of a marginal because they start to bolting. But the length is still is okay. They're not longer than 2 inch in length. But this is the example I don't want to show in the bolting. I don't want to get confused with compactness because you have to look at both, in the field. So this one, this is not marketable. Even it's marketable for bolting, but compactness are 1. They're not marketable, just for your information. If you look into 4 and 5, those are clearly not marketable. The bolting, they're getting really pointy and getting long. Specifically for level 5, you can clearly see they start to flower. You don't want to harvest lettuce when they're that old. You can clearly see, it's really hard. Those are the image we grade by our eyes. So it's really time consuming. So that's why I want to come with this idea. How about we use machine learning? So we come with this model, you can automatically grade for those 2 quality parameters. So for my material method, I have a training set and validation set, very typical for machine learning. Because it's the first time I do this kind of analysis, so I didn't try a lot of image, but so I tried 20 image for either bolting or compactness at each level I use for training. And for validation, I have 5 image, either bolting or compactness at each level for validation. I ran into the problem, those are the images that are previously graded by my professional, which is my colleagues. But I ran into the problem, sometimes, there are very limited image of either 1 or 5 bolting or compactness because they are the stream level. So it's really hard for me to find image. So in occasion, I only have maybe 2 to 5 images for training, and worst situation, like I only have 1 image for validation. But this is the best I can find for training this model. The training model that uses CNN is known as convolutional neural network. It's called CNN. CNN has different layers for feature analysis, for feature extraction. First will be convolutional layer, which is recognize features in pixels. Second one will be pooling. Pooling is a summarization of all the features. So by feeding this model more images, you actually get more information. So the summary will be more ideal. You get more feature by summarize using pooling. Lastly will be fully connect. Fully connect if you have a new image you want to do the grading, they will actually look at the feature of interest and they will mix and match what are the similarity. And that it will give you this different percentage. For example, we're looking for compactness. This is the example of compactness is about 1. So they will give you the percentage of grading for 1 will be, if it's more higher accuracy, they will tell you there's 90% chance we're thinking this is 1 for compactness. And there are different level for 2, 3, 4, 5, but they're relatively lower than that. You want them to be significant. So higher number for what you're looking for. Here you train the model. You have 2 individual models, either for compactness or bolting. And after that, we'll do the validation step for accuracy. I want to specifically send my friend Wang. He actually graduated from UNL with computer science background. He's really comfortable like working with machine learning. So we've been working together for like a month to come up with this model. So let's move on to the results. For the results, this first one I want to show is for compactness. Our accuracy is not really great. It's about 66.7%. Most of the error is fall into reading for 1 because I don't have a lot of image for extracting the features. So it makes sense for that. For 4 and 5, there are also not good prediction, especially a lot of 4 is wrongly predict as a 5. If you pay attention looking at the compactness, we're looking on that top layer. For 4 and 5, this is the key feature. So the computer, they're smart enough to look at the top overlay, but they're not getting enough information to separate 4 and 5. So this is the error that I find. Moving to bolting is really similar accuracy. It's about 68.4%. The error is fall into 3, 4, 5. 3, 4, 5, you remember the bolting, we're actually looking at the pointiness. So in this example, the machine, they're actually able to detect the pointiness, but they're not able to measure the length. They don't have enough feature to, actually more accurate to separate the differences. I just want to say, if you look at my accuracy, it's about 60%. That's not too bad. You have 20 images for training, but I'm just saying, I'm not nearly close, just give it to my boss using that for the company. I'm not that confident. Looking at this, behind this data, the percentage I tell you, the probability for 1, 2, 3, 4, 5, it's all about 20%. It's more like you're rolling a dice with 5-sided. They're not really significant for each other, so it's not really good for detecting the differences. So I would like to work more with them, get more images. So for training, for discussion, I mentioned that I have very low accuracy. That's due to the number of images for training is low. That will, not providing enough feature information for the model. And also there are very limited data for either 1 to 5 for bolting or compactness. So I recommend, for the company, maybe they can purposely harvest the letter when they're really young or really old, so they can get the image. That way they can make the model more robust, so they're able to detect all the differences in rating. Looking into the literature review, I really recommend you have at least more than 100 images for training. The more the better, especially for the Black Pine pest, they have more than thousands of images. That's why their accuracy is really good. It's 95% accuracy. Another issue that I encountered when doing training for this is the image that we're taking at RD-FRAG, they're not used for machine learning. They're more used for taking the image and then we grade by professional. We just look at the image. So it's not really good for doing the cropping, because some of the grades are different at different dates. This is the example, we have 10 letters in the grid, but then we might change the grade, we have 12 letters. So it's really hard for me to come up with the automatic cropping system. So I have to do manually crop it. It take me a couple of days, just to crop them one by one. And also, if you look at some of the letters, they're overlaying on each other. This is not good. You cannot use this image because it doesn't give you the features. So sometimes you cannot use certain image. And also, this number is on their way too. If you try to crop this image, you have to get part of the paper that tell you the plot number, and that will confuse the computer. They might think that's one of the other features that they have to look into. So that's maybe cause low accuracy. Another example will be sometimes if you don't clean the table really well, you have plant debris. They might also confuse as some features for for the lattice. So now we're finished my chapter 1, 2, 3. I just want to talk about what are the general challenge for image analysis. There are extrinsic factors. Extrinsic factor including complex background, that including you have excessive green elements or plant debris and soil, that I mentioned before. When you take quality image, you have to avoid this. Also, the lighting condition, we're taking image in the field. You cannot control the lighting condition. Sometimes you have overshadowing. You have a really brightness condition, especially around noon. Those are not ideal. Intrinsic factor for image analysis, including sometimes you deal with disease with no defined boundaries. Those including powdery mildew. Sometimes they don't have really defined boundaries. Hard to do feature correction. Also, there are like disease, stress, toxicity. They all share really similar symptoms. So you have to know what you're doing. You have to have the expertise. The differences. You want to know what are the causes. So you don't want to confuse yourself with different disease with similar symptoms. Excuse me. And also, we might have a hybrid symptoms. So sometimes if you have a plant that got infested with 2 or 3 disease, they might show as completely new symptoms. That will confuse you when you do this kind of image analysis as well. Lastly, will be the cost of the equipment, especially for hyperspectral image. The cost is really high. It's about easily like $10,000 above, and some of the equipment they're just really expensive for people that they can afford to do this kind of analysis. So hopefully in the future, the price for hyperspectral image or other camera can be a little cheaper. In summary of my whole 3 chapters, I want to say, first of all, you want to maximize the quality of image, especially, the higher the quality you take at the first place, the less you have to mess around doing image processing. Second of all, you have to be really familiar and understand image processing for image analysis. You have to have experts that match the specific method to what you're looking into. For example, NDVI is really good at detecting yellowing. For machine learning, you also need to require expert that are comfortable working with this kind of data. So the number of label images is very important. You want to have more image for training that will give you more features. And then for algorithm, there are literally like paper that they test 12 different algorithms. They don't know the difference between algorithm because there are thousands of paper based on the algorithm. So it's hard to see which one is better for the other. So they're testing 12 different algorithms. So sometimes if you do this analysis, it's better to look into the literature review, find something you're doing similar. That will give you kind of like knowledge which kind of algorithm is better for you to use. And now I'd like to end my presentation, and I would like to take a moment to thank my committee, Dr. Gary Hein, Dr. Sam Ortman, Dr. Lauren Gisler, and Dr. Jerry Adams. I really appreciate my committee, especially for Dr. Adam. I really appreciate, he's just retired, but I really appreciate the early time that he heard the mentorship from him. I also want to specifically thank Dr. Gary Hein and Kylie White. English is not my first language. I really struggle at the writing process, especially editing. And I make so many mistakes that, for example, algorithm, I cannot spell it wrong, but I cannot even be able to tell the differences. So I really appreciate the patience, that the mentor from them, they're willing to work with me. I just really appreciate that. I also like to thank my fellows, past and current DPH students, also my friends and family here in the US and in China. And lastly, I want to specific thank to my RD for Ag company family in Yuma. I know nothing about image analysis 3 months ago. Now I'm comfortable, giving a presentation, talk about image analysis. So I really appreciate the encouragement from RD4Ag. They really taught me well. I want to show you some of the good memories I have at RD4Ag. Here's an example of my boss, Steve. We're doing corn rootworm evaluation in Yuma. So he's using the Coursera, taking some image. We're constantly trying to, innovate image analysis process as a company. And here's me having a good time planting peppers. And summer is really hot in Yuma. How hot it is? I was making herbicide. You see our clock is starting to melt. It's really warm there. This is the example, an image that we took at Grand Canyon. So Steve really showed the hospitality, showed me around Arizona. If you go Arizona, you have to go to Grand Canyon. So I had a great time there. And here's the image of us, the whole team. The first time I was there and the second time I went back. I really had a good time. First time I really didn't want to leave. I cried a little bit, and my friend called me Chillon, which is Spanish mean for crybaby. So I love the company. They not only they tell me new things about doing research, but also they tell me how to be a better person. Taking responsibility of doing research. So I just want to specifically thank my family in RD4Ag. With that, I'd like to end my presentation and really thank you for your attention. Thank you so much. Mm-hmm. Yeah.
How does the sampling that you might do, like,
Mm-hmm.
so I can't sell this. So how do you harvest right? You want two labor and working. How you
Okay. So the question from Tim is the sampling timing, right? So how?
sampling that you're seeing testing.
Oh, okay. So the sample size of your measuring in the field. So to ensure that we try as more as possible, but our plot is smaller plot is 40 feet long. So we usually measure what in between. So it's 20 feet in the center. That's having more effect because we're doing reduced fertilizer study for some of the image. So we're measuring what is in the center. So that will be around 20 to 30 height of lettuce. That will actually, we're able to differentiate the difference between the treatments. So I think around 20 to 30 is a good number for us. Yeah. So yes, that's correct. Yeah. Entire plot will be 40 to 60. So we're measuring the center because the center has more of the effect from the treatment. Yeah. But that's a good question. Yeah. Okay, I have two questions online. Question one for Chris will be, for your lettuce work, as the current human rater trained each season, and do they compare intra and inter-rater score for standardizing compactness and bolting result of raters? For this, for training by rater training, Steve made a really good presentation of how you look into the features. So we have a standardized quiz that we have to take. So not only look into the features, we have about 20 slides. Each slide has about 20 letters. We have to rate either for bolting or compactness, and there's a exam after that. So we're doing a really good training process that will take us about a week to actually making someone more comfortable. So that will actually avoid this intro and inter scoring, for this type of, and as like grading. I hope that answered your question, Jeff. Second question is by Chris. He said, how do you bright the gap between contract research using to on-farm use? This is a good question. I would say, definitely would be better, if farmers can work together with contract researcher. We at RD4, I'm pretty sure, Steve always like to share with farmers. So sometimes we recommend farmers come over to our farm. We're not, trying to hide something we want to share to people. So at RD4, we have farmers come over there. We show them, we have different systems for drip irrigation. We really like to teach them this information. The contract research company, they're always at their meetings. So sometimes my boss, he's part of the board member of the specialty crops in Arizona. So he always give a good talk, sharing this kind of information. So I guess, the communication, having conference, able to share your knowledge to farmers will be very important for, sharing the technology. Okay, Lindsay has a question. I mentioned counting insects and cite a 2001 paper. Do you think it's possible to accurately count mites, such as weaker mites? I definitely think we can actually design, research like this. I have an example that I did with whiteflies, but mice are more smaller than that. You have to have better system, more higher resolution image. But it is possible, you can take really high quality image and you can count this number of mites by professional first, and then you pair it with the image feed to the algorithm. I definitely think there's a lot of place, you can actually, possibly come up with the model to count mice in the weaker mice in image. So I definitely think it's doable. I have a question from Gang. Doing machine learning and analysis, how do you decide the number of layer and the neuron in each layer? Machine learning is not really my expertise, but I know for CNN, there's generally you have 3 layers. I don't really know how many neurons in each layer. Yeah, this is kind of all of my understanding. So I'm sorry, I got more of word from my friends Wang, so I don't know much detail about machine learning. We do, yeah. Oh, the question is, when we do the destruction sample, do we worry about potential? You mean the debris on the lettuce? Oh yeah, like the way you slice the lettuce, you have to be standard in the center. That would probably really minimum, because we're not taking a couple of days. We have a bigger crew. We usually just do it right away, really fast. The whole morning we just finish everything. We definitely don't do it when it's really hot. We usually do it early in the morning. So, the humidity is relatively higher. So yeah. I'm thinking about, we also like standardize cutting the lettuce. We want to do perfect in the center. You don't want to, you kind of curve a little bit. That will definitely affect the quality of the image as well. Dr. Yitzer? Dr. Gutser has the question of, when you are deciding if it's ready to harvest, do you go there and, measure it, sending people sample it, or there's a way you can just look at internally? My answer would be usually the big farm, they have different manager. They will send people in. They will actually randomly cut lettuce from different spot really quick. 5 minutes, they just cut the lettuce and then they size it. They see if it's okay. They just go send the crew and harvest it. So they usually just do like some random sampling before they harvest, make sure that it's ready. But this is a work that is more applicable when we're doing reduced fertilizer study at the company. So we want to see the treatment effect on the internal quality. Yeah.
Chen.